Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Design of Coastal Structures for the Protection of Ponnani Coast Parasakthi PB Superscript 1, Neha Mohammed Sadik Superscript 2, Gayatri Menon Superscript 3, Dixon Devassykutty Superscript 1 Superscript 2 Superscript 3b. Tech Scholars, Department of Civil Engineering ADI Shankara Institute of Engineering and Technology, Colleague, India Dr. P.K. Suresh Visiting Professor, Department of Civil Engineering ADI Shankara Institute of Engineering and Technology, Colleague, India Abstractes an effect of sea water rise and storm surges caused by the global climate change. The coasts are subjected to rapid erosion along with anthropogenic activities. Severe erosion leads to land loss, flooding and building loss. In this paper we are designing a seawall as well as an offshore breakwater at the Panani coast situated in Malappuram district of Kerala to prevent further coastal erosion which happened due to various factors involving coastal hydrodynamics, storm surge as well as due to the effect of the cyclone Ockhi. The effect of rising sea levels, frequent storm surge, frequently occurring cyclones have eroded the coast drastically up to 15 m according to the data collected for the past few years. As a measure of beach management, these coastal structures of appropriate length were designed after collecting adequate wave data and tidal data from various sources. The seawall is designed according to the Engineering Manual 1110-2-1614 for the length of 2100 m. The cross-section of the seawall is designed using AUTOCAD. The seawall is generally designed to consist of 3 layers that are core, secondary layer, and an armour layer. For beach restoration adequate breakwaters were also designed. Keywords: coastal erosion, seawall, breakwater. Introduction. India has lost about 1/3 of its coastline to erosion between 1990 and 2016, putting at risk more than 560 million people living in the coastal areas. Threats to India's coastline are set to exacerbate with the long-term removal of sediments and rocks along the coastline or the displacement of the land resulting from the action of waves as well as climate change, causing higher sea levels, unpredictable precipitation, and frequent storms. Various methods such as construction of groins, detached seawalls, anti-sea erosion bunds, offshore breakwaters can be formed using sand-filled geosynthetic tubes/bags etc. are generally taken to prevent erosion. The coast of Panani situated in the Malappuram district lost 15 m of its beach due to coastal erosion. Dozens of houses along the coast of Ponnani and adjacent areas were damaged as the turbid Arabian Sea carved into the coast at the places where the seawall was missing as the coast suffers from the strong action of waves, high tides and storm surge. The cyclone Ockhi also gave a drastic push in the process of erosion. As this is a severe coastal erosion, a seawall can be chosen as the first and the most suitable coastal structure that can be designed. Seawalls are vertical, general, or massive concrete structures placed along a considerable stretch of shoreline at urban beaches. From the data we realize that reducing the effect of the waves with which it hits the shore as well as controlling storm surge flooding can greatly reduce erosion. Thus designing a new seawall as well as an offshore breakwater can be the best form of coastal structure and the best measure chosen for proper beach management. A seawall is a wall or embankment erected to prevent the sea encroaching on or eroding an area of land. There are mainly 3 types of seawalls: vertical, curved and mound. Design of a seawall consists of 4 layers: an armour layer, a core layer, a tow mound and a bedding layer. A breakwater is mainly a barrier built out into the sea to protect a coast or harbour from the force of wave. Rebuilding the beach that we lost all these years is also possible through the construction of these 2 coastal structures due to sediment deposit brought forward towards the shore by the force of waves on the structures. 2 objectives to conduct desk studies to design a seawall. To design a breakwater. 3. Methodology 3.1. Study area identification. The study area selected was the coastline near Panani in Malappuram district, along the centre coastline of Kerala. Ponnani is a seashore town situated at the mouth of Bharatapuzha, bounded by Arabian Sea on the west and estuaries and backwaters on the northern side. The coastal town is located around 10,046 feet 3 inches N latitude and 75,055 feet 30 inches E longitude. The major fishing harbour of Panani is situated in the mouth of the Bharatapuzha river. The average elevation is 5 meters above MSLA 30 m. Lighthouse is situated near the shore, which was commissioned on April 17, 1983. Fig. 1, Satellite imagery of the Panani coast, source Google Earth, IJERT 10 is 060323 www.ijert.org 695. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 3.2 Desk studies. The satellite imageries of a coastal stretch provide useful information concerning the shoreline changes and, if available over a number of years, may be superposed to understand the effect of natural/man-made interventions on the shoreline changes. The shoreline behavior adjacent to protruding land masses will serve as an indicator for the direction of net alongshore sediment transport. For the present analyses, satellite imageries adjacent to the shore-connected structures were collected, analyzed, and the direction of sediment movement was assessed. A location near to Lighthouse is fenced and marked for analyzing the changes undergone by the shore. It is near to the Ponnani Harbour, which is at a distance of approximately 1051 m, having mouth of length 236 m and jetties of length 386 m. Fig 4, Google Earth satellite imagery of January 17, 2015. Fig 2, Google Earth satellite imagery of December 08, 2009. Fig.2 clearly shows the longshore current, which is a powerful transportation agent transporting longshore drift, or littoral drift, in action on the fenced region, having a beach of length 10.57 m and a seawall was constructed for preventing erosion. Fig 5, Google Earth satellite imagery of April 12, 2017. Fig.5 shows significant changes in the shoreline. The sea can be seen invading land and complete loss of beach up to the seawall is observed. A loss of about 15 m width of beach is observed. Fig 3, Google Earth satellite imagery of January 05, 2012. Fig.3 shows no significant changes in shore from 2009 to 2012. There is still considerable beach area. Fig.4 shows an increase in beach area due to accretional process. Due to interventions to stabilize the shoreline such as seawall, reduced erosion rate was observed. Fig 6, Google Earth satellite imagery of March 21, 2018. Fig.6 shows the image during the year 2018. It can be observed that complete destruction of seawall near the lighthouse occurred during cyclone Ockhi, which was the most intensive tropical cyclone in the Arabian Sea, happened on November 2017. The shoreline reaches the land area and there is a significant loss of land over 5 m as well as destruction of the compound wall of Panani Lighthouse. IJERT 10 is 060323 www.ijert.org 696. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Fig 7, Google Earth satellite imagery of April 01, 2020. Fig.7 shows the changes happened to the site. A new seawall was constructed which prevents further erosion. The width of seawall is found to be 9 m. The overall analysis showed that the entire coast is eroding, even though there were some places with accretional processes seen due to the effect of sediment from river inlet. Some areas in coastal zone were found to have deposition of sand, but mean rate of accretion were less than that compared to erosion. Cyclone Ockhi has severely affected the shore, resulting in land loss and destruction of seawall. The coastal stretch of Panani Lighthouse is located at about 2 kilometers north of river inlet. This river brings lot of sediments into the sea. 2 training walls are constructed at confluence point and it results in direct discharge of sediments during rainy season. As the sediments are not allowed to settle along the coast, it is not getting transferred to adjacent beaches by waves. This is also one of the reason for beach erosion. 3.3 Wave data. The wave data of Ponnani coast, which belongs to grid No 8, were taken from Wave Atlas Table 1. Offshore wave data for grid 8 month January, February, March, April, May, June, July, August, September, October, November, December. Wave direction W.R.T north 340 340 330 300 300 270 270 270 280 300 340 340 average wave height, m. 1.5 1.5 1.5 1.6 1.8 2.5 2.5 2.5 2.5 1.5 2.25 1.5 wave period, SEC, 77777.5 7.5 7.5 7.5 7.5 3.4 tidal data mean high tide equals 1.6 m mean low tide equals 0.1 m average tide equals 0.9 m 3.5 design of seawall 1. Design procedure water depth equals 0.50 m tidal height equals 0.90 m storm surge equals 0.50 m mean sea level equals 0 total maximum depth equals 0.50 plus 0.90 plus 0.50 equals 1.90 m water the maximum possible sustainable wave height in a particular water depth is, maximum wave height, Hmax equals 0.78 times water depth equals 0.78 times 1.90 equals 1.48 m. 3.5.1, the design water depth can be calculated from the mean water depth, tidal level, and the water level set up during the storm. In the calculation of armour weight, the design wave height, represented by significant wave height is needed to be established. Significant wave height, HS equals Hmax / 3.5.2, 1.8 equals 1.48 / 1.8 equals 0.82 m slope of seawall seaside equals 1 in 3 land side equals 1 in 1.15 crest elevation equals MSL plus high tide plus storm plus HS equals 0.00 plus 0.90 plus 0.50 plus 0.82, 3.5.3, equals 2.22 m add freeboard equals 2.78 plus 2.22 equals 5 m2. Structure design armor layer Hudson formula was used for the estimation of the stable weight of armor rubble stone, W50 Wr times 350 equals, 1, 3 times the following rubble characteristics were assumed. The unit weight of sea water, equals 1025 kg/m3. The unit weight of armor, equals 2650 kg/m3. IJERT 10 is 060323 www.ijert.org 697. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06. June 2021 The stability coefficient, KD was adopted to be 2.0 slope angle of layer equals 1 in 3 2650 times 0.82350 equals, 2106525 1, 3 times 2 times 3 equals 61 kilograms but provide minimum of 1000 kilograms or 1 t. The nominal median diameter of stones corresponding to the armor rubble stone weight can be calculated using 50 equals 51/3 1130 equals 2650 equals 0.72, 3.5.4, equals 1000/10 equals 100 kilograms width of toe mound equals 2 times HS equals 2 times 0.82 equals 1.64 m or equals 0.4 x d equals 0.4 x 1.90 equals 0.76 m adopt 2.0 m provide height equals width/2 equals 2/2 equals 1.0 m, 3.5.7, 3.5.8, the thickness of armor layer, T, can be calculated using T equals N times KD times D. Assume number of stone layers N equals 2 layer coefficient KD equals 1.15 we know, D equals 0.72 m T equals 2 times 1.15 times 0.72 equals 2.0 m top width equals 2.0 m provide. Top width equals 4.0 m, so as to move vehicles. Bedding layer minimum thickness equals 0.50 m provide 10 kg to 1 kg core layer weight of stone equals W/200 to W/4000, 3.5.5, equals 1000/200 to 1000/4000 equals 5 kg to 0.25 kg provide 10 kg to 1 kg toe mound. A toe mound is to be placed on side of the seawall preventing the sliding of the stones and protecting the seawall from slope failure and scouring. Weight of toe mound equals W50/10, 3.5.6, Fig 8, cross section of a seawall 3.5. Design of an offshore breakwater design as per Japanese Manual for Construction by Coastal Engineering Research Center CETN 3-23. It is an empirical method based on the survey of 1,500 projects from 1983 to 1985. Depth of breakwater proposed, D0, equals 1.50 m. Located 15 m from coast. Assumed slope of the coast equals 1/15. Total land loss in the form of beach from lighthouse to river equals 300 m. Average width of beach lost equals 15 m. IJERT 10 is 060323. www.ijert.org 698. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Hence in the project it is proposed to create 15 m of salient wave period considered equals 7 sec. Wave height adopted equals 1.25 m. Wave length at 1.5 m equals times L.S.W equals 7 times 9.81 times 1.50 equals 27 m. Calculation of breaker depth using deep water wave equation. Deep water wave length, L0 equals 1.56 times T2 equals 76 m. 0 equals 1.25 equals 0.016076. Estimate breaker depth equals 1.40 dB equals 1.4 times 1.25 equals 1.75 m. As per reference, based on the slope, beach is in type C equals 1.5 equals 0.86 1.75. Calculate salient aspect ratio, SAR, parameter from reference here. SAR for 0.86 equals 0.70. Salient development expected equals 0.70 times 15 equals 11 m, which is nearly the lost width of 15 ma. Calculation of ranges of length of offshore breakwater LS for type C, 1.42.33.8 LS62b, length of breakwater based on the distance from shore. Distance from shore equals 15 mx as per reference for type C, 13.51553 from equation 1 and 2, adopt. The range as follows: maximum of lower value and minimum of higher value. Average equals 38 plus 53 equals 91/2 equals 46 m. Adopt the length as 46 m. Length of breakwater is 46 m ls and length of coast is 300 m lc as per reference 2 lslc. Adopt the following expression for gap between breakwater lg based on length of breakwater ls and distance from shore x 0.7 1.8 0.7 15 1.8 11 27 based on length 0.5 1.0 0.5 46 1.0 23 46. Adopt maximum of minimum range and minimum of maximum range 23 27 23 plus 27. Average equals 2 equals 25. Design between offshore breakwater equals 25 m. Provide 4 offshore breakwaters with 2.5 m spacing. The cross section can be designed using Hudson's Formula 1. Design procedure: water depth equals 1.50 m, tidal height equals 0.90 m, storm surge equals 0.50 m, mean sea level equals 0 m. The design water depth can be calculated from the mean water depth, tidal level, and the water level set up during the storm. Total maximum water depth equals 1.50 plus 0.90 plus 0.50 equals 2.90 m. The maximum possible sustainable wave height in a particular water depth is, maximum wave height, Hmax equals 0.78 times water depth, 3.6.1, equals 0.78 times 2.90 equals 2.262 m. In the calculation of armour weight, the design wave height, represented by significant wave height, is needed to be established. IJERT 10 is 060323 www.ijert.org 699. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org. Significant wave height, HS equals Hmax /1.8 equals 2.262/1.8 equals 1.26 m. International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021, 3.6.2. T equals 2 times 1.15 times 0.72 equals 2.0 m. Top width equals 2.0 m. Provide top width equals 4.0 m, so as to move vehicles. Slope of breakwater 1 in 3 crest elevation equals MSL plus high tide plus storm plus HS equals 0.00 plus 0.90 plus 0.50 plus 1.26 equals 2.66 m. Add freeboard equals 2.78 plus 2.66 equals 5.44 m, 3.6.3, 2. Structure design armor layer Hudson formula was used for the estimation of the stable weight of armor rubble stone. W50 from equation W_50 equals WR times HS3, slash, S_R1, 3 times K_D times cot. The following rubble characteristics were assumed. The unit weight of sea water, W_S equals 1025 kg slash M3. The unit weight of armor, W_R equals 2650 kg slash M3. The stability coefficient, KD was adopted to be 2.0. Slope angle of layer equals 1 in 3 W_50 equals 2650 times 1.263, slash, 2650 slash 1025, 1, 3 times 2 times 3, equals 221.7 kg but provide minimum of 1000 kilograms or 1 t. The nominal median diameter of stones corresponding to the armor rubble stone weight can be calculated using D_50 equals W_50 slash W_R, 1/3, equals 1000 slash 2650, 1/3, equals 0.72 m, 7.14. The thickness of armor layer, T, can be calculated using T equals N times KD times D. Assume number of stone layers N equals 2. Layer coefficient KD equals 1.15. We know, D equals 0.72 m. Core layer weight of stone equals W/200 to W/4000 equals 1000/200 to 1000/4000 equals 5 kg to 0.25 kilograms. Provide 10 kilograms to 1 kilogram. Toe mound. A toe mound is to be placed on side of the seawall, preventing the sliding of the stones and protecting the seawall from slope failure and scouring. Weight of toe mound equals W50/10 equals 1000/10, 3.5.4, equals 100 kilograms. Width of toe mound equals 2 times HS, 3.6.4, equals 2 times 0.82 equals 1.64 m or equals 0.4 xt, 3.6.5, equals 0.4 x 1.90 equals 0.76 m. Adopt 2.0 m. Provide height equals width/2, 3.6.6, equals 2/2 equals 1.0 m. Bedding layer minimum thickness equals 0.50 m. Provide 10 kilograms to 1 kilogram. Fig 9, cross section of a breakwater. IJERT 10 is 060323 www.ijert.org 700. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 4. Conclusions. The coastline is the separation of the land from the sea, thus protecting or maintaining that borderline plays a very important role in maintaining the natural eco-balance. Hundreds of millions of people are migrating to the beaches in quest of a better living, and the coastal and marine ecosystems provide very important services. If the coastlines are affected due to natural or man-made reasons, immediate measures need to be taken to prevent them, reduce them, as well as rebuild those lost coastlines if possible. The coastline of Ponnani was one of the coastlines that was facing the threat of erosion. Design and construction of appropriate coastal structures can not only help to control erosion but would also help to rebuild the lost areas of the beach gradually. Thus, for the coast of Panani we chose to design 2 coastal structures. A seawall to prevent and control erosion and a breakwater to protect port infrastructure from the destructive forces of the waves while also providing calm conditions for the ship's berthing. Acknowledgement. We thank Dr. P.K. Suresh, Visiting Professor, Department of Civil Engineering, ADI Shankara Institute of Engineering and Technology, for expertise and assistance throughout. References 1M 1110-2-1614 Design of Coastal Revetments, Seawalls, and Bulkheads, June 1995, 2 Coastal Engineering Technical Note CETN 3-23, Rev 395, 3R. Sundaravadivalu Sakthival P.K. Suresh Remedial Measures to Combat Sea Erosion Along West Coast of India ICOE 2019 Foreshore Protection Manual, Volume 1, 2, Coastal Engineering Research Center, Department of the Army, Waterway Experiment Station, Corps of Engineers. 5. Anu Murali Coastal Protection Measures for Shoreline of Mumbai Review and Case Study International Journal of Engineering Research and Technology 2026 Professor V. Sundar Dr. K. Murali Planning of Coastal Protection Measures along Kerala Coast Department of Ocean Engineering Indian Institute of Technology Madras IJERT 10 is 060323 www.ijert.org 701. This work is licensed under a Creative Commons Attribution 4.0 International License.